So let's look at another example of taking a Laplace transform of a time domain function. So like always with these examples, I would encourage you to pause the video and maybe try to work it by yourself before coming back and seeing the solution. So as these equations get more and more complicated, there's not necessarily going to be one correct way to do it. There are a variety of ways and properties that we can use. So I don't want you to think that you have to be searching for one specific way. So in this case, we see we have f of t equals t squared sine of 2t times u of t, and we want to take the Laplace transform of this. So just like with last time, in our previous example, this u of t is just defining our sine times t squared for t greater than 0. So just defining for t greater than 0. So again, in some textbooks or some locations, you might not see that explicitly written, and that's perfectly normal. So looking at this, we see we sort of have these two main components, our t squared and our sine of 2t. So what I would say is, well, we know the Laplace transform for our sine, so we actually spent a lot of time showing that. But even if we hadn't done that, we could of course go to a table of common pairs, and we could say, we know Laplace transform of sine of 2t is going to be omega divided by s squared plus omega squared, where in this case our omega is 2. So omega is 2, omega squared is 4. But what are we going to do about this t squared term? So what we can recall is that in the time domain, if we're multiplying, so let me write this out first. So if we have our time domain, if we have a -1 in t to the n multiplying by our other terms, what that corresponds to is taking the nth derivative in the frequency domain. So this was one of the operational transforms that we had looked at. So since we have a t squared, then we know that must mean that we had two derivatives. And so that also checks out, because if we have -1 squared, then that's going to be just 1. So let me write that explicitly. So we can say n equals 2 in this case, which of course corresponds to a second derivative. Okay, so what do we actually do then? So let's come down here. We can say that our f of s, which is the Laplace transform of that function, so Laplace transform of t squared sine of 2t is equal to the second derivative with respect to s of whatever the Laplace transform of the thing being multiplied by t squared is. In this case, that's that sine of 2t, and as we said above, we know that was 2 divided by s squared plus 4. Okay, so I'm going to rearrange this a little bit just to make it a little easier to see. So I'm going to say this is the second derivative with respect to s twice of 2 times s squared plus 4 to the power of -1. So all I've done is just rewritten that so it's a little easier to take this derivative. Okay, so let's do one derivative at a time, of course. So if we've taken one derivative, we still have a derivative with respect to ds left. So the -1 comes down, so we have -2. That's multiplied by our s squared plus 4, and we increment that exponent to -2. And from chain rule, looking inside that parentheses, we have a 2s coming out. Okay, so again, to make this a little easier, I'm going to rewrite it again. So we have d ds of, now in the numerator, we're going to have -4s, and in the denominator, we have s squared plus 4 quantity squared. Okay, so again, we're going to sort of go back to some old rules that maybe you've not used in a while, but what we're going to use here is something called our quotient rule. And so from our quotient rule, we can say that this derivative is equal to, so if we have, this is our high and this is our low, what we have is low, so s squared plus 4 squared, times d high, so derivative of high, which is negative 4, minus high, which is negative 4s, times derivative of the bottom, so that's going to be 2 times s squared plus 4, and then again from chain rule we have the 2s coming out, and then all of that is going to be divided by log squared. So we have the quantity s squared plus 4 to the power of 4. So again, that quotient rule is basically low d high minus high d low over low is sort of a mnemonic device to help you remember that. Okay, so let's simplify this a little bit then. So in our numerator, we see we have this s squared plus 4 term in both of these terms. So let's go ahead and factor one of those out. So we can say s squared plus 4, and after factoring that out, we still have an s squared plus 4 in this first term, and that's being multiplied by negative 4. In our second term, we now just have the negative 4s times 2 times, and so, times our 2s. So we get something that looks like that. And we've not done anything with our denominator yet, so that's still s squared plus 4 to the power of 4. And so of course what we can see here is that we can cancel out this s squared plus 4 with one of these in the denominator, so this becomes s squared plus 4 quantity cubed in the denominator. And so we can just collect terms in the numerator to find that our Laplace transform of that function is equal to 12s squared minus 16 divided by s squared plus 4 quantity cubed. So that would be our answer. So you can see it sort of takes some practice getting familiar with the transform pairs, the properties, how to use the table, but once you get the hang of it and once you're able to spot it, it's not too bad. So the next thing we're going to talk about in the next few videos is how do we take the inverse Laplace transform? So how do we go from here to our function in time? And so as we've already said, we want to avoid using that ugly equation, so we're going to talk about in more detail how we can do that.